thank you for inviting me to give a talk at Arizona and amazingly at 2 universities simultaneously. And I visited both universities and I like both of these places. So my talk today will be mostly about two-dimensional charge density wave quantum materials and devices. But before I go to this main talk, I would like to highlight a few other research directions which we have in my group, and maybe, yeah, just also emphasize the importance of investigating materials and maintaining expertise in this area for future devices, whatever they would be. And for some reason I cannot switch. Oh, okay, I can now. So I'm coming from UC Riverside. Riverside is one of 10 UC campuses, which you probably know. And if you look at the nature pictures in Joshua Tree Park or in UC Botanic Garden, you would see some similarities with Arizona. And I would like to say that in recent few years, Southern California is becoming more like Arizona because people are replacing the typical traditional landscape with Arizona-inspired landscape, which takes less water. I also would like to acknowledge students who contributed to different aspects of this work, starting from Guanzhong Liu, who did the first device work with tantalum disulfide, and most of these guys are now happily employed at industry, at Intel, Apple Corporation, Keysight, etc. So I put this slide as a summary of different research activities in my group at Nano Device Laboratory and Photon Optimized Engineering Materials Center. It also gives me opportunity to brag about some of the recognitions. So we have conducted the first work on thermal conductivity of graphene and addressed some fundamental physics properties of photon transport in this material. Now this work evolved in the direction of practical application of thermal management. And so I will also flash a few slides to show what we are doing along this line. The new direction of research, which started to push this area, this particular field in about 2014. However, it now became sort of mainstream already, only recently. And this is what I call quasi one-dimensional van der Waals materials. And so I just received the Van der Waals Bush Faculty Fellow status, which comes with substantial funding, which would allow me to go into details of quantum effects in these materials. And we also have a joint project with Stanford on discovery of new Van der Waals materials, computational-driven discovery. In other areas, nanoscale photon engineering, nanophononics. And in this area, in my lab, I have a range of experimental setups to measure thermal conductivity, thermal diffusivity of different materials, big or small. And also, in addition to Raman spectroscopy, we have Bullion spectroscopy, which looked at the acoustic phonons. And then our approach is to combine knowledge of acoustic phonon transport with thermal conductivity and acoustic phonons as the main heat carriers in many materials of interest. And I already mentioned Raman and Bullion capability, and right now we're developing a unique instrument, Bullion-Raman Mandelstam spectrometer, with funding from NSF MRI. We would like to build a really advanced instrument which would allow us to look at acoustic phonons and magnons in low-dimensional van der Waals materials, which have small lateral sizes, and many of these materials come as small lateral sizes. And yet, one last direction of research and capability I would like to mention is that low-frequency electronic noise. We measure low-frequency current fluctuations in different materials, and we try to go beyond this, trying, reducing noise. We use noise as a spectroscopy tool to learn something about material, electron transport, and traps. And right now I'm part of the Arizona State University EFRC Center, Ultra, led by Bob Nemanich, and there we work both on thermal conductivity measurements and also on using noise spectroscopy to assess quality of wideband gap semiconductor devices. And if you're curious about research directions, I have a well-updated website, which is the address here. So just now, I'll go faster with a few slides to to tell what we have done and what we are doing. So yeah, we developed this Raman optothermal technique in order to measure thermal conductivity of graphene. And the idea here, this is illustration from MateriAlZ spectrum of this method. We suspended graphene over trench in a silicon wafer, and we use the laser of a Raman spectrometer as a heat source. So by increasing power of the laser, we were able to heat up locally graphene suspended over trench, and we could measure local temperature by observing the shift in the GP position. And with some calculations, then you can figure out what's thermal conductivity in this material. And this technique now became popular. Many people adopted it and improved it, and it has been used for various two-dimensional materials. And as I mentioned in my group, we are now moving towards practical application. And one of the problems with the conventional electronics, of course, is heat removal. In order to maintain this decrease in size, increasing frequency, you have to come up with thermal interface materials which conduct heat better. Right now, commercial materials have, which are epoxies or non-cured, they have thermal conductivity on the order of 10 watt per meter Kelvin. You have to go beyond that. And so one of the direction of research for us is to come up with composites and which have graphene and boron nitride fillers in order to control electrical and thermal properties independently. And here you see this is epoxies. The white one is this boron nitride, which is electrically insulating, and black one is this graphene, which is electrically conducting. But what we have found, you can achieve thermal percolation, and that is when increase in thermal conductivity becomes superlinear, even before electrical percolation. So that's one of the lines of research here. And just to give you a few examples, if you look at this is non-cured thermal paste, which we used with some advanced Intel CPU, some desktop, and by removing commercial thermal paste and putting our thermal paste with graphene, we were able to increase the CPU temperature by 10 degrees Celsius. Another advanced application of graphene is the thermal management of battery packs. Thermal management of battery packs is done differently than of computer chips. Typically, industry use thermal phase change materials, PCMs. PCMs absorb heat rather than conduct it away. In our approach, we try to preserve the ability of PCM to absorb heat, but also increase its thermal conductivity by adding graphene flakes. And this results of cycling of battery packs with lithium-ion batteries show our material gives you advantage compared to what's commercially available. And I'd like to sort of summarize this this thermal thrust in our research group by saying that, yeah, we're still waiting, expecting key applications for graphene and electronics, and I'm hopeful that they will come. But you can also keep in mind that in thermal field, they're already entering or entered market. And if you're curious about state of that in graphene thermal field, I recently wrote a brief perspective overview of phononics of graphene related materials, which includes some fundamental things, phonon transport, but also goes down to practical applications. Okay, so that was about graphene thermal field and related thermal management field. And as I already mentioned, today most people talk about two-dimensional materials, but now I also have a very active research thrust on van der Waals materials, which have a one-dimensional motif in their crystal structure. So now just to explain the terminology, I call van der Waals materials, and conventionally in case of two-dimensional case, you have a layer which has strong covalent bonds. Then between the layers, you have weak van der Waals bonds. And of course, first example is graphene, but then you have transition metal chalcogenides like MOS2, and in this case, so you have a tri-layer which is strong covalent bonds, and then you can exfoliate and you have a quasi two-dimensional material, right? However, you can also think about other group of materials. Example of them are transition metal trichalcogenides, and they have strong covalent bonds in one direction, but in perpendicular planes, they may have van der Waals bonds or weaker covalent bonds. And in this case, you can break down these materials into atomic chains, or bundles of atomic chains, which would be needle-like. And so, and this is essentially also van der Waals material, but it has distinctly different geometry. So this is what I call quasi one-dimensional material. And so that's the concept that we were developing from time. On the left, you see the picture I adapted from Gaiman Grigoryev review when they talk about exfoliation two-dimensional materials and then putting different ones and making heterostructures. But you can also think about quasi one-dimensional van der Waals material that there is like pencils in a bundle, and you can break the bonds, and you have now the separate pencils, and you can also mix and match, and you can do heterostructures, and there's a lot of flexibility with this. But you can also use sandwiches which have 1D and 2D van der Waals materials. So what's peculiar about those? The first property which we introduced, and I think that kind of brought some extra interest to this field, is that they can have very high breakdown current density. And here, this first experiments we had we did in 2015, 2016, this quasi 1D tantalum triselenide, and you can see we measured accurately cross-section area with AFM, and you can see that the breakdown current density here could be up to 32 mega amperes per square centimeter, which is 10 times that of magnitude for copper measured by the same DC stress. And of course, they have Voss resistivity. Resistivity is higher than for elemental metals. However, other groups also without the special now showed that the scaling of resistivity in van der Waals materials is very different. So when you scale it down to very small dimensions, resistivity is not increasing very high, like in case of copper or other elemental. So in principle, there's a hope to find another quasi 1D material which would have high breakdown current density and simultaneously low resistivity. And I think that that would be a big deal for electronic industry that is looking for new materials for interconnect. We also demonstrated the use of such quasi 1D materials in composites for electromagnetic interference shielding. So what you see on the left is this material, and you can notice needle-like structure of crystals of these materials. And because the aspect ratio of these materials could be extremely high, and there is no problem, like in case of carbon nanotubes, with control of what type of conductivity there. And so it performs amazingly great as a filler for electromagnetic interference EMI shielding. In this particular case, we managed to do electrically insulating film, which was soft, yet it absorbs extremely well electromagnetic energy, so it can work as the EMI shield, both in gigahertz and even sub-terahertz ranges. And the mechanism of shielding here is different from conventional, from metal. Metal is just reflecting back to the environment. This one absorbs it. And these results are published in Advanced Materials in case you are interested along this line of research. So that was my sort of overview of what things we do. And now I have time, and I'm moving to the main topic of my talk. I will try to get you interested in charge density wave materials and devices. So this is the outline of my talk. I will give a little bit of physics background, and then we'll tell you about how we can use these effects to construct devices which can operate at room temperature. And I will explain all the interesting properties of those. And this work was mostly funded by my individual PI grants from DOE. Okay, so what are the charge density waves, just in case some people have not heard about them? So if you take certain metals which have quasi 1D crystal structure, so here we go back from 1D to 2D, that have quasi 1D crystal structure, it can become energetically favorable for them to when you start cooling them down, to develop a lattice distortion, which would be then accompanied by periodic modulation in electronic density. And this is essentially was noted initially by Pierce. And he thought that maybe it's not too practical. And as far as I understand, didn't even publish a separate paper. He entered this paragraph in his textbook. And this displacement could be really small, typically less, than 1%. However, they're sufficient to induce this modulation. It's now modulation similar to what you have in superlattice, right? As a result, you're opening a band gap, and so you're opening a band gap at Fermi wave vector. So you have a wave vector of this this modulation would be 2kF, and this modulation has been confirmed in many studies by scanning, electron tunneling, etc. And essentially, what we are doing here, this is a macroscopic quantum phenomenon with which this high coherence length. And so, what were typical manifestation of the effects in these materials? So the classical work, so charge density wave, was popular topic in 70s, 80s, 90s, including the following. So what I'm showing here, that you take a material which has this transition, in this case it's tantalum trisulfide, you cool it down, and now, so it enters a charge density wave regime. And by the way, so we have to say here, because the wavelength of charge density wave is defined by the Fermi level, it doesn't need to be commensurate all the time with crystal lattice. So, and if you have incommensurate state, so the charge density wave can slide. However, typically in any realistic material, you have defects and boundaries of the sample. So this charge density wave is pinned by defects, so it's not sliding. I would like to emphasize here that this is actually a quantum mechanical state, quantum phenomenon, because this is manifestation of the wave nature of electrons in order to create this modulation in charge density. And essentially, and it also many electrons condense to the state. So it's many body phenomenon. So now what was happening in typical experiments? So if you start applying bias, initially you have a little current, and this current is just current of individual electrons because charge density wave is pinned. But on a threshold field, the wave starts to slide. And as a result, you have this nonlinear current conduction, strong increase in current, and simultaneously, you also would have now AC component in current. So you'll have some oscillations. You can illustrate it with some models. So if you look at the left, no voltage applied. So regular metal, you can use this charge density wave. It's just okay, one particle. So it's standing on a flat surface. And in case of charge density wave, so it is in this modulated potential, like the area for X we use. So now if the voltage is low in regular metal, you would start having current, right? But here, this voltage may not be sufficient yet to induce the motion of this particle. At higher voltage, so in regular metal, you just have regular increase. But here now, the particle would start moving. And that means that this onset of collective current of charge density wave, which also comes now with oscillations. Okay. And in the 80s, there were a number of proposals for different devices. But the problem was that, including from Bell Labs, but the problem was that this is all temperature things. So most of these materials, which revealed this charge density wave effects, required cooling them down to temperatures below 200 Kelvin. And the regular, at the same time, you can make a beautiful oscillator. It's just a piece of material, a terminal device. You apply bias, and then you have this peaks at megahertz, and that is able cold narrowband noise, and not correct term because it's actual signal. This is time varying signal from moving charge density wave. Okay, and again, the biasing circuit for this oscillator would be very simple because frequency is proportional just to the current that you're passing. So that was in early days. Now, at certain point, the interest charge density waves obviously could not compete with silicon CMOS, etc. So only hardcore physicists were working on it. But then I think that there was a change starting from 2000s. And here's I give example of one paper from 2008. And the interest from one side, those who worked in charge density wave moved to new group materials. And as I myself personally, because I worked with graphene and 2D materials, and I thought, well, what kind of, if just MOS2 is just a semiconductor, right? But can I have a transition metal chalcogenides, which would have some fancy properties if I thin it down? And one of these materials is 1T tantalum disulfide. 1T means 1T polytype. So if you look at the resistivity of this material as a function of temperature, you see that it undergoes through several transitions. So at low temperature, around 180 Kelvin, there is a transition to the commensurate charge density wave. It's also accompanied by more insulated transition. And you have a hysteresis. You go up and down in temperature. Then at 350 Kelvin, you have transition from nearly commensurate regime here to incommensurate regime. Incommensurate regime when you don't have inflation symmetry. And then it becomes normal metal at temperature about 550. Okay. And of course, like physicists, we're mostly interested in this low temperature transition. It's you can probably it's probably easy to understand the physics there, etc. And I'm sorry. And if you look at this I took from one paper I saw online. This is also clarifies a little bit the structure. So when you have this is 1T tantalum disulfide from the side view, you have this layers and then van der Waals gap. This is top view. And when you go to mental transition, so you have distortion in the lattice, and lattice distortion here is that the tantalum, 12 tantalum atoms move slightly to the 13th atom that forms sort of like a David star. And in this material, there is no abrupt transition from metallic state to commensurate charge density step. So it undergoes through several intermediate steps. So one intermediate step is nearly commensurate when you have a domains which is commensurate with this new crystal structure periodicity, and it's surrounded by incommensurate phase, which you can think about as a sort of domain walls. And you also have incommensurate phase when you're losing translation symmetry, which is closer to metallic. Okay, so now dimensionality, thickness of these materials also play a role, because in this work of from other groups, they show that if you change the thickness of this film, the transition temperatures may change. And that is because going to charge density wave phase is interplay, how much energy you spend to distort the lattice and how much energy released to go to new ground state. So of course that balance would depend on thickness. And initially my group started to work with 1T tantalum selenide, and we looked with Raman spectroscopy how we can move material up and down at different thicknesses. And the point of transition we could observe from Raman spectrum, because when you go to incommensurate phase, translation symmetry disappears and Raman peaks become flat and wide. Okay, and I don't want to go too deep in the physics, but I'd like to just say that the physics of charge density waves could be very different from materials with one-dimensional motif that people studied in bulk form and two-dimensional materials. So in 1D case, it's described by Pierce model, but in 2D case, we have the different physics, and we still would need to have a strong electron filling up. And there is also some relevance to superconductivity, etc. But I was interested as a primarily engineer in possible device application. If I have this fancy material, which I can call quantum, even at room temperature where it's already in millicommensurate regime. I see a question in the chat.
Alex,
yes.
We can address the questions after the talk.
Okay.
Sorry, I told you. I think what we ask people to do is to post questions, and after the talk, you can.
Okay. All right.
Sorry about that.
No. So, and I was interested, well, can I play with some phenomena in this material and make devices separate from temperature? In order to do that, we use two approaches in my group. So one is that we use electron beam lithography, and for that you need to have a flake. You cover it with boron nitride, which is like capping layer. Then we can etch through metal contacts. And the device itself is essentially to thermal device. Okay. We also use now shadow mask. For some cases, it works better, and it just allows you to make more devices. What's important to verify the quality of contacts, because it's non-trivial task to make good contacts to this materials, to this group of materials. This is traditional method, shell coordinates. And in this particular case, as you can see again, picture shows green is a bond nitride capping, and we have a channel, and these are metal contacts. You can see that wet chip contact, we verify contacts, etc. So afterwards, what you have to do once you have this terminal device, you can start applying stronger bias. You have more current, and you hope that you would see all these fancy things. Now, people knew that yes, you can, if you just have small bias, you change temperature, you can move device from one phase to another. Now, but when you apply bias, you can also move the material from one phase to the other. Now, what's mechanism of transition? From one side, it could be just pure electrical field. Electrical field can induce transition from one phase to another. But of course, another mechanism which you can never exclude easily is that by passing current through this device, you also produce Joule heating, local heating, and you can have local temperature increase so that it's enough to just switch material phase. And again, I'd like to emphasize, I probably have said several times, this is not just regular resistive switching device. In many resistive switching devices, you have to apply much higher currents, and you also actually melt one phase into another. Here, lattice reconstruction is tiny, and that could be fast and low power because of that. So now I would like to show you. So if you look at the left, again, we are passing little current, this small bias, so that it's close to equilibrium, and we're changing temperature. And you can see, because my student made this film very thin, below 10 nanometers. Oh, I forgot that size of 10 or 20 is critical. So then transition, this more inflated transition at 180 degrees disappears, just like other people reported. But the transition between nearly commensurate and incommensurate at 350 is still there. It's very robust transition. So now my idea is that, okay, can I use this hysteresis to get some device functionality from this quantum material at room temperature? And I'd also like to emphasize, we're not doing like a regular resistive switch where what's important is on-off ratio. Here, I'm just using hysteresis window to get functionality. And if you look now at the current of this typical device, in performance device, apply bias, and this is current. And this, what you see, this hysteresis is the same one which you see on the picture on the left. And this is two different devices, different dimensions. You can also see there is some onset of superlinearity here. And as we discovered, we explained it, proved it now, this is not onset or sliding of charge density wave. This is actually local heating. Okay? But now I'll say, okay, can I do device functionality? And this is, and my idea was, I'm just giving you if, but, well, if I put the load line, if I put the resistor in series, I put the load line, it goes through this hysteresis, then I can get oscillations, quite stable thing. This is like negative feedback. All right. And this is summary. I have to watch my time. Summary of our old work. This is an H&N paper. What you see here, this is current as a function of voltage at different temperatures, and low temperatures is window. And this is again my transition from commensurate to incommensurate, the one which appears at 350. So at low temperatures, window is large. When you're increasing to room temperature, you still have decent window. And of course, it disappears when you get close to 350. And we proved that directly that this is indeed this transition, because so in one case we measure this resistance as a function of temperature. The scale here a little bit offset, so this happens at 350. We can check what is resistance here and here, and then we measured by applying voltage, and we proved this is a slope gives resistance, and we put that resistances, we proved that resistances match. So I'm indeed playing with this transition between two phases in charge density waves, nearly commensurate, which is and could be viewed as a polycrystalline kind of grains. So you have islands of commensurate phase separated by incommensurate, and these islands can melt. to incommensurate. And I'm playing this transition between nearly commensurate and incommensurate phase. So now, I mean, it's easy to make an oscillator now. So this is my device, active device. I put the resistor here, and you know, it's like electrical engineering sort of circuitry. So when my bias exceeds certain threshold field, my tantalum disulfide switches to a high conductive state, current increases, and then voltage drops on RS increases. So I don't have enough, and the process continues as long as I keep it here. And as you can see here, this is oscillations, just get from oscillator. If your bias is not enough, there's no oscillation. When you have enough bias, there is oscillation. If you're too much, it's also no. Okay, so you just have to keep your load line within this hysteresis window, and you have oscillator. This case, oscillator oscillates in megahertz region, but this is limited by parasitics, and in fact, it would be fast. And then we did 3 integrated device, which consist of 3 different 2-dimensional materials, and we are using specific intrinsic functionality of each material. So we're not trying to use bandgap and graphene or anything like that. Graphene here is acting as a voltage-controlled resistor, and for that you don't need to have a bandgap. So the way how it works, you can see here, this is one tantalum disulfide active device. It's connected in series to graphene FET, which is just voltage-controlled resistor. I can change resistance of graphene by applying gate bias as a stop gate device, and boron nitride layer acts as a cap layer on tantalum disulfide, and it's gate dielectric on graphene side. And you can see now, you know, I'm applying gate bias, and I get oscillation from this thing. So this is beautiful voltage-controlled oscillator, which operates at room temperature, and that is essentially a quantum material and quantum device. And you can see this nice thing that frequency is a linear function of gate bias. So that was the result. And I already mentioned that we use noise spectroscopy to say something about phase transitions. I would like to skip this part because my time is limited. But essentially, we measure the noise response in this low frequency domain. It's from 1 Hertz to 100 kilohertz. And this is very informative. So it's sensitive to defects, which act as trapping centers. And it's also sensitive to phase transition. When something happens with lattice, I mean, noise peaks, okay, by using this property. Now, of course, when we did this device, people ask, what's good about this device? How can they compete? One of the possible competition is radiation hardness. So if we are going to move to Mars anytime soon, we need to have electronics which is radiation hard against X-rays and protons. Our conventional semiconductor devices are not radiation hard because damage created by X-rays or protons gives you trapping center, and trapping center takes electron away. You increase noise, and of course also charge accumulation, the interface can shift the threshold fields, etc. So what you look at here, this is this hysteresis window, which I'm using for my device functionality. And we sent the devices to Vanderbilt University, and they put a very large dose, X-ray dose. And even after this big X-ray dose, the window voltages did not shift. I think it was a shifting by 2%. So it's very radiation hard. And the reason for that is the following. Some people claim that graphene FETs or 2D FETs are radiation hard. Not really, because your charge neutrality point will go like crazy under any radiation. You know, the argument that just radiation goes through doesn't really work well. But in this particular case, this is metal. It's the first case, and we are switching between 2 metallic states, high carrier concentration. As a result, if you have a trap that which takes electron away from channel, nothing happens because carrier concentration is very high, and it's also 2D geometry, and we don't care about Dirac point or anything like that because this is a essential to terminal device driven by resistor series. Okay, and as you can see here, we send device to Vanderbilt. They send us back, and it still oscillates very well. So before radiation, after radiation, so that's again this emphasis. But of course, that people say, well, that's good, but protons really that's what things. So in order to shield conventional electronics, you use metal shielding, which makes it heavy. And so if it be radiation part against proton bombardment is a big deal, and that's what we proved. So you can see again this working windows of the strong proton bombardment and large dose. IV did not change, so it means that oscillate would oscillate the same way. And now we used our low frequency noise spectroscopy also to show sometimes some damage from radiation cannot be seen easily in IVs, but it would be seen in low frequency fluctuations. And so you can see that there is very little change. This is noise level before and after. Okay, now because again I have to watch the time, I would like to say we use then noise spectroscopy further to observe all the transitions. And one of the things that let's say the transition to metal state has very little change in resistivity. Let's say right, like if you look at the left picture, so this is transition from nearly commensurate to incommensurate, and this is transition from incommensurate to metallic, very small change in resistivity. However, noise is very sensitive. So if you look at this picture of spectral density, the function is the same electrical field to be applied. So this is your nearly commensurate incommensurate transition, has strong peak. And then we also have strong peak again, incommensurate to metallic transition. And we thought, okay, our noise spectroscopy is a good tool to check properties of materials and phase transitions. What we also proved by using devices with different geometry, that the transition to the classical design, when you have just dimensional charge adjusting material on silicon oxide substrate, this is still Joule heating induced. So it's not pure electrical field effect, it's still Joule heating. So we're only applying bias and current, even though bias in our case is much smaller than in typical resistive switching things and currents. We still produce enough heat for material to switch. That's our switch. So then the question we had, it still doesn't mean that you cannot achieve conditions when it will be pure electrical switch. And in this case, it might be very fast device. But our question was that if this switching is driven by local heating, can it still be fast? And we collaborated with a group, as a word in University of Buffalo to prove that. So for that, we sent them devices which were fabricated on special substrates, special feeders, and they did measurements with pulse measurements, starting from a few nanoseconds and then increasing. So when you just start with, let's say in this case, so on the left is experimental data, on the right it's our simulated data. So when you start with very short pulses, it does not, and pulse has the same amplitude, it does not produce heating. That's why you don't open hysteresis. But once you increase it, you see the hysteresis starts to open. So this is experimental data. This is simulated. We just simulated electron and thermal transport simultaneously using COMSOL. So the model was validated. Then, so you can see this is hysteresis width, this is simulation, and this is experiment. So the trend is the same. The fact that they're different in their height is not that important because we characterize hysteresis just by difference in opening and closing voltage. And also we don't take into account some etc. But now once we have this experimentally validated model, we decide to say, okay, if my device would be smaller, which would be comparable with our silicon CMOS, then it would take me less to heat up the sample, right? So we took this validated model and we'll check what would happen if you optimize the device size and device size. I see that you can hear me, right? Okay. If you optimize device size, and in this case, we showed that you can go to very small pulses, which would correspond to gigahertz switching speed. So in principle, so even if these devices are driven by heating, they can be fast. And now, since I have a limited time, I was asked to finish around in 11:45. I'd like to say that briefly, but still we were wondering why in IV curves for two-dimensional materials we do not see this kind of abrupt current increase like in this classical papers on charge density wave effects and bulk crystals with quasi-1D crystal structure. So they had this, say, if you look at this picture from George Gruner's review, so you see that a threshold There is a strong increase, right? And we don't see it. Well, we have slight increase. Initially, we thought maybe that when you have this onset of superlinearity, this is onset of charge density beginning. So, but so far our functionality was based on just this hysteresis, phase transition between commensurate and incommensurate. But can I do functionality in two-dimensional device with sort of like deepening and sliding of the charge density waves, like people did previously? And we saw that. We also look at the noise and we see some abrupt increase here. We thought that must be deepening, okay? But we couldn't prove it conclusively. And that was puzzling us for quite some time. And at some point, we increased the frequency domain, and at some point, we saw, oh, we do see these peaks in megahertz frequency range, like in older days. And moreover, the peaks frequency increases linearly with the current. We thought, maybe that is exactly the same what people observed for ND selenide-3 at low temperature, and we have now the same thing, functionality based on now sliding of the wave, not on just hysteresis, but also on sliding, because it looked very similar. But it turns out Roger Lake, a colleague of mine at Riverside, with calculations his student modeled, it turns out, no, we're just hitting on this device again, this hysteresis, and that's where oscillations come from. However, we continued playing with that, and we finally just recently figured out. So if you look at this IV curves, and more carefully now, I'm looking at the region, which is still linear, right here. And at this region, I was expecting the strong increase in current. And I have only slight increase in current. However, if you take, you don't see anything. However, if you take a derivative, so you have to accumulate data points with enough data points. Take a derivative of IV characteristics. If something happens, a small bias. See, the bias is very small, 0.14, I think it's here. I forgot. So something happens, and there is something serious in forward and reverse. So something, if we don't see it on IV curve, but something actually happens here. And we used also our power of low frequency noise spectroscopy. And we see that noise at this point increases tremendously. And it also evolves from 1/f to having some bulges, like arranging bulges. You can see this is now noise spectral density as a function of bias voltage. Exactly the same bias voltage. We have this huge increase. And you see there's several orders of magnitude because there is a break in the scale. And hysteresis, and everything coincides with what we see just by derivative of IVs. And we thought, well, that must be something related to charge density wave now moving into two-dimensional materials. And so this is now noise spectral density multiplied by frequency to get rid of the 1/f background. And we now clearly see some Lorentzian bulges which start moving, and their motion also approximately scales with the current. So now what we're seeing that we believe that we did discover now movement of charge density wave in two-dimensional material. However, it's very different from what people had in quasi 1D materials, because here you have these islands, and the motion of charge density wave, the contribution to current is still very small compared to current through the incommensurate incommensurate. It's like a river with islands. So contribution from incommensurate phase, the current conducts, is much higher. That's why in IVs we don't see this abrupt increase in current, and it also takes much higher fields to start this motion. So the bottom line, you can probably come up with some functionality, but the physics still requires explanation here, and could be very much different from what we have in sort of like traditional charge density materials with quasi 1D crystal structure. And I'm coming to conclusions here. So we came up with devices, switches, which have functionality completely different from transistors, also different from resistance switching. And this the functionality is based on quantum mechanical phenomena, which could be observed at room temperature and has high degree of coherency, so the samples could be large. We also proved that low frequency noise spectroscopy is a powerful tool to look for not just for the quality of materials, but also for phase transitions. These materials may have very different and radiation hard properties. which could be good for some space travel. And we think that there are other 2D and 1D van der Waals materials which may have superior charge density properties, including room temperature and above. And I would like to acknowledge again the funding from DOE project on 2D, and also on from NSF. It's on finding new materials. And I would like to stop here. Thank you very much.
Thanks, Alex. I think we have time for some questions. And I think we already have a couple of people have posted it. So let us start with Priyadarshini. Priyadarshini, if you want to switch on your speaker and ask the question.
Should I just read and answer?
Yeah, if you don't mind.
Oh, okay, yeah, I can do that. So the first question was how much different is a commensurate charge density wave and nearly commensurate charge density wave state. And so I showed you a picture. So in order to achieve the commensurate charge density wave state, you need to cool down material below 200 Kelvin. And so it's low temperature. So resistivity is higher there. And and you have a periodic arrangement. Nearly commensurate could be viewed as islands of commensurate phase separated by incommensurate phase. And as you can see, again, resistivity is different. And the transition from one phase to another is accompanied by big hysteresis, which is larger than the one between nearly commensurate and incommensurate. And now, in terms of theory, description of electronic transport, it's very difficult to understand that, because when you have a region where it's incommensurate, so there's no translation symmetry, it's difficult for theoretical guys to model it. Okay, now there's would you say that the noise spectroscopy is better than measuring electric constant when it comes to define phase transition? I think electric constant diverging is there. Okay, I wonder if is less than. Okay, so that's a very good point, because these materials can have a huge dielectric constant. That was one of the interests. Now, I think that noise spectroscopy is just complementary to optical methods. So when you do something with optical method, at least you are studying something with the spot of a laser, right? So and laser would be more than a micrometer here. So noise spectroscopy device could be small. I just need to get signal, and I think that there could be also transitions which may be more observable with noise spectroscopy than with optical means, dielectric constant. Because dielectric constant would probably change when you have phase transition, but deepening and sliding of the wave probably is better, probably easier to be detected with noise spectroscopy. And now,
okay.
I think that I read the questions which were that. Right?
Yeah. So anyone else who has questions, feel free to ask the questions now. I think we have a few more minutes left.
I have a question. You show that the commensurate CDW phase at the transition of mod temperature will have a larger hysteresis. So the question is, why do you want to do the device at the transition between the near commensurate CDW and the incommensurate CDW?
Okay, yeah, that's a picture which many people reproduce, including my group. I just love this picture because it put it very nicely. Indeed, this hysteresis is much larger and change in resistivity. However, I do want to have something which works at room temperature. That's my first motivation.
I see.
And the second one, I also explain you. If I want to go to nano, probably any device now has to have nanoscale. And this large hysteresis at low temperature actually disappears. You see, this is work from, I put this work from other people. We also achieve the same results, so completely proven. So as you can see, it starts from bulk and goes to small dimensions. And at the order of 9 nanometers, this hysteresis disappears. However, the other one still persistent. And you can see what we also did here. Let's say, see, this one device was seen, the series disappears. Or let's say here, that's you can see that transition at room temperature is robust, but the other one disappears. So our results are in line with this. So that's why, to summarize, I'm curious to play with effects which can be seen at above room temperature, and it's kind of interesting to have a quantum material and quantum device at room temperature. From the other side, also this big hysteresis disappears, but when device thickness becomes smaller than 9 nanometers.
Mm-hmm. Thank you. Gotcha.
Mm-hmm.
Anyone else?
Krishna, can I ask a question?
Yeah, of course, Ankit. Go ahead.
Yeah. So yeah, great talk, Alex. This is really not my area, but I certainly learned a few things here. So I have a question about the cutoff. Is there really a cutoff in terms of the irradiation damage that irradiation, especially in terms of, you talked about Mars exploration. So is there something like a cutoff we know of where these devices, the performance of these devices really becomes concerning?
Oh, okay. I thought there are two things I forgot to mention about frequency. So first of all, this frequency which we played with, megahertz, it's not really limiting. It's just equipment, right? And we, using this physically validated, experimentally validated model, we showed that frequency could be very high, gigahertz range. So that's about frequency cutoffs. But now about what you mean, the limits at which radiation hardness breaks down, right? That's And to tell the truth, we don't know, because Vanderbilt University, which are the group which is, these are experts in Fleetwood, they use maximum dose. They use maximum dose for X-ray and for protons, what's available. And as you can see, the devices were amazingly robust. Now it probably would take some theoretical guy to do computation and explanation, but so we are limited in terms of what's dose available or energy is available.
I have also a connected question about this. So, of course, when we talk about exploration, we have multiple, like irradiation is one of the aspects. Other aspect could be, say, for example, on Earth, we have a pH of air, which is about 5 or 6. So we are happy with all these devices working. But say NASA may be interested in Venus exploration, which has clouds of sulfuric acid. So you have a highly acidic atmosphere. So is there like any systematic study, or is this something a semiconductor industry is interested in, where they want to also address the corrosive environment and its effects on the semiconductors?
Well, that's a good point. And I think that for many 2D materials, if you have this ambient, which is tough ambient, that can act as a sort of like chemical doping, right? That's why people use graphene as a sensor. And it makes sense because in these 2D materials, you have highest surface to volume ratio, right? And you have high sensitivity of electron transport, depends on Fermi level position, and it could be changed by its ambient molecules, etc. I think that here we are less susceptible to this because, again, it's metallic and high carrier concentration. We did not manage to also gate it, and I think many other people also tried. You can easily gate graphene, but you cannot gate this one, which suggests that it's probably would be less sensitive. And another thing, you can use boron nitride capping naturally here, like with any other 2D material, and we have demonstrated this possibility. So in this sense, I think that it would be also pretty stable in a tough chemical environment.
Yeah, that's good. Yeah, thank you. And again, thanks for accepting our invite. This is great.
Thank you.
Any other questions? I'm not even sure if it's a really good question, but I was wondering, like for the charge density waves, just like how for like electronic conductivity and thermal conductivity in metals are connected through the Lorentz number, is there a equivalent for a charge density current? Like would it, when we are thinking about thermal versus electrical conductivity of a charge density wave?
Well, again, this is interesting question. I think that there have been studies in, again, all the days in 1980s where they observed abrupt jumps also in thermal conductivity,
Oh, okay.
which were connected with phase transitions.
Yeah.
So I'm assuming that if electrons are dominant heat carriers, and maybe there is some contribution from charge density waves, but I haven't studied it myself. I think it's interesting possible direction of research as well. Yeah. So people studied thermal conductivity of charges only in this bulk crystals with quasi-1D crystal structure. I'm not aware of any studies in this 2D charge density.
Okay. Cool. But there's lots of other questions. I think we can discuss it when we meet. Any other questions, folks? Or I think we are edging. We have 2 more minutes, so let us know if you have any other questions, or maybe I can ask one more pertinent questions. So, do you think that this? I mean, if there's technology realization of this, I mean, what do you foresee in the future? Would you think that this could replace silicon CMOS, or
Okay.
going to be a complementary?
No, all right. So I I don't want to say anything bad about silicon CMOS, right? I think it's, to me right now, it's just very fascinating material system, and I'm not that much worried with practical application as yet.
Okay.
But everybody looking for another switch, which would not be transistor switch.
Yeah.
And I think that if we can control this charge density wave effects, we will find the way how to control them better with the gate, not just with applying source drain bias. That could be a good candidate for possible new switch, because again, all the things which propose is the use of quantum phenomena, right? Other than its optics, they typically go to very low temperature, and the quantum state are fragile, etc. This one is robust. That's what makes me excited about it.
Cool. Okay, I think we are right at 12 p.m., Alex. So thanks a lot for your time. I know that